Okay, let's jump right into this explainer on the engineering behind the DeepSeek V4 model. We're looking at a highly constrained, seriously resourceful team here. They didn't have unlimited compute, yet they still managed to build this open source architecture that's literally going toe to toe with the closed source giants. For all you software engineers tuning in, the architecture and custom GPU kernels we're about to unpack are an absolute masterclass in optimization.
Here's our engineering breakdown for today. We're going to cover 1. An impossible engineering feat. 2. Solving the cache bottleneck. 3. Preventing catastrophic explosions. 4. Pipelining custom kernels. And 5. The ultimate efficiency payoff.
All right, Section 1, an impossible engineering feat.
Just look at this massive number right here, 1.6 trillion. That's the parameter count. And, at this sheer scale, just holding the model weights in memory is an extreme infrastructure challenge all on its own. But honestly, that's only half the story. The second part of the challenge is the context window. They built a short-term memory capacity of 1 million tokens. To put that into perspective, that translates to roughly 750,000 words. Imagine feeding an AI the entire Harry Potter series, the whole shebang, and then asking it to perfectly recall a specific tiny detail from a random page without completely choking the hardware. At this scale, standard attention mechanisms just completely fall apart.
So, moving on to Section 2, solving the KV cache bottleneck. Instead of perfectly memorizing everything one word at a time, the DeepSeek team engineered this brilliant hybrid attention bypass that basically splits the workload into 3 parallel pathways. First up, we've got compressed sparse attention. This groups tokens into small chunks and uses a super fast internal search engine, the Lightning Indexer, to grab only what's absolutely relevant. Second, heavily compressed attention aggressively squashes 128 tokens at a time to maintain a broad, high-level summary of the whole document. And finally, they use sliding window attention to keep the most recent tokens in uncompressed, perfect fidelity. It's kind of like a clever student cramming for an exam, right? They rely on high-level summaries of old chapters, but keep the current page perfectly open right in front of them. The result of this hybrid architecture is absolutely astonishing. By asking the elegant engineering question, how little can we process, instead of the brute force, how do we process everything, V4 requires 3.7 times fewer compute flops than the previous DeepSeek 3.2 version. Think about that. It's running on just 27% of the compute. No way, right?
And the staggering efficiency payoff here is on the memory side. Because of that 3-tiered hybrid system, they successfully shrank the short-term KV cache memory footprint by 90%. They literally eliminated 90% of the gigabytes that normally just sit there, idle, clogging up expensive GPU memory. This entirely alters the hardware deployment reality for open-source models. It's a total game changer.
Which brings us to Section 3, preventing catastrophic explosions.
Now, when you stack dozens of neural network layers at this massive scale, you run headfirst into a terrifying math problem. Activation signals start to amplify exponentially, kind of like terrible microphone feedback. So how on earth do you stop a 1.6 trillion parameter network from exploding? Standard residual connections, those bypass lanes that let signals skip layers to stay stable, they simply aren't enough to prevent these catastrophic signal explosions at this extreme scale. The team literally had to design a very strict mathematical rulebook to fix this. Enter a novel architecture called manifold constrained hyperconnections. They force the residual signals onto a manifold of what are called doubly stochastic matrices. Okay, so what does that actually mean? It means every single row and every single column must perfectly sum to 1. Because of this strict constraint, the total signal is completely conserved. It literally cannot amplify. They're forcing the signals into this perfectly balanced state before any pressure can ever build up, mathematically forbidding the training run from crashing.
To further guarantee a nice, stable convergence, they actually threw out the industry-standard Atom W optimizer. Instead, they built their own custom Muon optimizer. Muon tunes the model in 2 distinct phases. It makes fast, coarse-grained updates first to get close to the target, like rough tuning a guitar string, before switching over to sweet, fine-grained adjustments to perfectly lock it in.
Moving along to Section 4. Pipelining custom kernels.
So the math is mathematically beautiful on paper, but we still have to move all this data across actual GPU racks without idle latency. To ensure 0 wasted milliseconds, the developers perfectly choreographed the data movement, breaking the transfers into sequential waves. Look at how this works.
The network cables stay completely saturated, ferrying Wave 2 data, while the GPU cores are simultaneously crunching the numbers for Wave 1. Computation and communication are perfectly overlapped. Thanks to this, network latency essentially disappears. Poof! To achieve this hardcore microscopic choreography, they went low level. They wrote custom fused GPU kernels in a specialized language called Tiling. By fusing multiple math operations together, they completely bypassed expensive, redundant GPU memory reads. And to make sure this highly complex code wouldn't introduce silent data corruption, they used a Z3 SMT solver to mathematically prove the code was 100% bug-free. Thanks to this insane level of deep optimization, the overhead for running those complex matrix constraints we just talked about using the synchron-NOP algorithm was shrunk to a tiny 6.7%.
Finally, let's look at Section 5, the ultimate efficiency payoff.
Now, how does this system behave with real data? Well, instead of overwhelming the model on day one, they used an expanding context curriculum. They started the model off at a mere 4,000 tokens to teach it basic grammar, and then slowly stepped it up, phase by phase, all the way to a full 1,000,000 tokens. They basically stretched the model's context horizon gently as its working memory stabilized.
But look, at 1,000,000,000,000 parameters, training is inevitably going to get a bit shaky. When the math threatened a loss spike, the model deployed this incredibly clever self-stabilizing trick called anticipatory routing. Instead of reacting to current, chaotic fluctuations, the model temporarily routes its decisions based on slightly older, historical snapshots of its parameters. It completely ignores the daily noise to lock onto the long-term trend, automatically stabilizing itself until the danger passes. How cool is that?
All of this elegant, highly constrained engineering paid off massively. DeepSeek V4 scored a perfect 120 out of 120 on the Putnam 2025 math benchmark. And let me tell you, that is notoriously one of the most brutal undergraduate math competitions in the world. Hitting that score proves definitively that this open source architecture can absolutely go toe-to-toe with the biggest, most expensive closed models on the planet. Which leaves us with this final thought for today's explainer. Seeing a resource-constrained team publish all these top-secret infrastructure breakthroughs and fused kernel optimizations for absolutely free really makes you wonder, doesn't it? When you strip away the billions of dollars of brute force compute, will clever, elegant open-source engineering ultimately win the global AI race? It certainly seems like the gap is closing a lot faster than anyone predicted.